to our Chemistry Wednesday tutorials that we normally have on Wednesday. Your presenter, as usual, is Teacher Kirwa. So this is our Chemistry Wednesday, being 1st of September 2020, at least in the second half of the year. So welcome all of you to our last lesson on structure and bonding. We have three past Wednesday already discussing on this particular topic. So today I would like us to wind up and then we start something else, God willing, next week. So all those who are I want to welcome you. I want to also take this time to thank all of you for the support that you have shown, for the sharing of the posts that you have done, the lessons that we've already done. So more is to come. So welcome. Feel free. If you have questions, as I always say, put them down there in the comment box, and you will get your answers right on time. So feel free and ask any question that you need. If there is any discussion you feel should be handled also as a student, you are welcome. All the members of the public, kindly let us share these posts. Let us help each other to welcome students into this forum so that this becomes of benefit to them. So welcome. Thank you. So let's get back to business. So in our last lessons, we have discussed ionic bond. We started by looking at ionic bond. We looked at the structure involved in ionic bonded compounds. We also did the properties of ionic compounds and all those kind of things. So that's what we discussed in our first lesson of this discussion. The second lesson of structure and bonding, we did covalent bond, that is last week. I mean the latest one is last week. We did hydrogen bond. So our second topic, we did covalent bond. We looked at the illustrations and the examples, the single covalent bond, double covalent bond, and triple covalent bond. In our third lesson, that is last week, we did hydrogen bonding and dative covalent bond, and the weak van der Waals forces of attraction. So that's what we did in our last lesson last week. We also looked at characteristics of those substances that have molecular structure and simple molecular structure and giant atomic or giant molecular structure. So we discussed about diamond, we discussed about graphite, we discussed about silicon oxide, and we looked at the uses of graphite and diamond. As we said, both of them are allotropes of carbon. So that is what we did. So today I want us to look at metallic bond briefly. Then we shortly discuss about the trends, and not trends, but the structures, properties of structures across period 3. Just briefly. So metallic bond. So as I said in our introductory lesson, that we have 3 types of bonds. That is ionic bond. This is just a preview or recap. So we said we have 3 types of bonds. We have ionic bond, which results from this ionic bond results from losing and gaining of electrons. That is, one atom loses an electron and the other atom gains an electron, or electrons can be one or many. The second type of bonding that we also talked about is covalent. Now in covalent bond, as we said, none of the atoms lose, but both of them share the electrons. This is where we said we have shared pair of electrons and we also have lone pair of electrons. So the covalent bond involves sharing of the electrons. Now the other thing we mentioned here is that we can have a special type of covalent bond, which we say is called dative or coordinate, where the shared pair of electrons are contributed by one atom. Otherwise, in covalent bond, the bonding atoms contribute equally to the shared pair of electrons. Number 3 is this one that we now want to look at, that is metallic bond. Now, in metallic bond, the atoms delocalize their electrons. So the atom delocalizes the electrons. In so doing, by doing all these, it leads to stability. So this leads to stability. Talking of stability, as we mentioned, stability involves the octet and or duplet. So when we say atoms lose electrons or lose and gain electrons, atoms share electrons, atoms delocalize the electrons. In so doing, they obtain an octet or a duplet, which is a stability of the group 8 elements. So in all of this, in bonding, this is what it involves, bonding entails. So let us look at metallic bond. That's our today's discussion. All right. So metallic bond, just as the name suggests, is purely for metals. This is purely for metals, and metallic bond is defined as the electrostatic force of attraction. Electrostatic force of attraction between the positively charged nuclei and positively charged nuclei of an atom and the negatively charged electrons, or the negatively charged electrons. That is the definition of metallic bond. An electrostatic force of attraction between the positively charged nuclei of an atom and the negatively charged electrons. When you say electrostatic or electrostatistics actually involves charges, positive and negative. So this is referred to as metallic bond, and as we have already said, the name suggests, it applies or it is applicable only in metals. It applies only in metals, that is metal atoms. For example, when you say sodium metal, it consists of several atoms of sodium. Okay. When you say magnesium metal, it consists of several metals of aluminium, of magnesium. Not several metals, but several atoms. So sodium metal, several atoms of sodium. Magnesium metal, several atoms of magnesium. Aluminium metal, several atoms of aluminium, and so on for the rest of the other metals. So what happens is you have we know that sodium loses an electron in order to be stable. So when it loses an electron, this sodium metal is positively charged. All the metals lose electrons. So sodium is positively charged. Now when it loses the electron, you know the electron is negatively charged. As we said, electrons are negatively charged. So what happens is, in a metal of sodium, you have the positive charges like that. Okay, let's assume this is a sodium metal. Now, each sodium ion here at least gives up and it delocalizes an electron. So this one delocalizes an electron like that. So you have electrons here. Okay, you have electrons around each atom. So now what happens is, these electrons, as we have said, are negatively charged. So each atom is attracted to these electrons, so that it looks like the atom is inside a sea of electrons. Okay, it appears that the atom is inside a sea of electrons. If we continue, we'll have other positive charges here. Of course, together with the electrons. So you realize, for example, if you look at this atom is, and you know, as we said, these electrons are delocalized. The electrons are delocalized. Delocalized means they move around the structure. They move around the structure. So every other electron is attracted to the positively charged nucleus. As we already know, the nucleus is positively charged due to the presence of protons inside here. So you see, it is attraction between the positively charged nuclei, these positive charges here, and the negatively charged electrons that are surrounding it. So that we are saying the atom, each atom is surrounded and attracted to the sea. Let us call it sea of electrons, attracted to the. So each atom is surrounded and attracted to the sea of electrons. To the sea of electrons. Sea of electrons delocalized around the structure. So every atom is attracted to the sea of electrons. I'm calling it sea because there are very many electrons surrounding each atom. So each atom is attracted to a sea of electrons. These electrons are delocalized around the structure. So that is how metallic bond is formed. Maybe we can also comment that this leads to formation of giant. This leads to the formation of a giant metallic structure. So that is it. So it leads to formation of a giant metallic structure. So maybe basically this is how metallic bond is formed. So we can look at the properties of metallic bonded structures. Maybe before that we can say the strength of a metallic bond is determined by the size of the atom and the number of the localized electrons. The strength of a metallic bond is determined by the size of the atom and the number of the localized electrons around the structure. You find that when we talk about, for example, the period 3 has sodium in group 1, magnesium in group 2, and aluminium in group 3. Okay, sodium, the valency of sodium, so the number of delocalized electrons an atom of sodium gives up is 1. Magnesium, 2 delocalized electrons. Aluminium, 3 delocalized electrons. So in short, we are saying now here that the strength of a metallic bond is determined by the size of the atom. In this particular instance, we said that when we were discussing periodic table, we say that the atomic radius decreases across the period. So in this particular case, aluminium has a smaller size compared to sodium. All right, aluminium has a smaller size compared to sodium. The reason we say this because of the increase in nuclear charge across the period. So in this case, size of the atom, aluminium has the smallest size, followed by magnesium, followed by sodium. Also, the number, so that means aluminium will have stronger metallic bond than magnesium, and magnesium will have a stronger metallic bond than sodium. The reason is here, the size of the atom and the number of the localized electrons. So you will realize that in this illustration here, in this illustration, we have said for sodium, one atom gives up 1 electron. Now, if it was aluminium, you find out one atom will give out 3 electrons. So this one alone, 3 electrons. This other one, 3 electrons. So for example, if we have, these are how many charges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, you will be having 15 positive charges and 45 negative charges. So the negative charges will be all over here. The attraction is so massive that it makes this metallic bond stronger than in sodium, than in magnesium. So if you look at for metallic bond increases across the period up to aluminium, because these are metals. The next one here, the next one after aluminium is silicon. So silicon is a non-metal. So now group 1, group 2, group 3 are what we are talking about. They have a metallic bond. So properties of metallic bonded structures. Properties of these metallic bonded structures. One is the obvious one. They are good conductors of electricity. Good conductors of heat and electricity. The reason why they are good conductors of electricity is because they have delocalized electrons. due to presence of delocalized electrons. So every metal is a good conductor of electricity because they have delocalized electrons. Number two is they are insoluble in water. Insoluble. Of course, the obvious reason is because they are not charged. They do not have charges. And then, so they are good conductors of electricity. They are insoluble in water. Also, they have high melting and boiling point. They have high melting and boiling points, of course, because this is a strong force of attraction. We have said metallic bond is strong, it forms giant metallic structure, and so it is the melting and the high boiling points are high because the stronger the forces of attraction, the more the energy used to break those particles, and therefore the higher the melting and boiling points. So that is metallic structure and metallic bonding, and that is the end of that bit. Okay, so next one briefly that I want us to look at is properties of bonds across the period. I'll only mention a few things there. Types of bonds across period 3. Types of bonds across period 3. Here we have talked about period 3 before, and we said these are atoms or elements that have that have 3 energy levels. So these include sodium, magnesium, aluminium, silicon, phosphorus, sulfur, and chlorine. So sodium is atomic number 11, magnesium 12, 13, 14, 15, 16, and 17. Okay, so types of bonds across the period. Let us begin with oxide. So I'll only discuss the oxides and the chlorides of this. So the oxide here, for sodium, you have sodium oxide, you have magnesium oxide, aluminium oxide, silicon 4 oxide, phosphorus, there are 2, we have phosphorus 3, 4. Yeah, we have PO. Okay. Let me write a good one. I can draw a table where we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, and chlorine. And then on this part, we have the oxide and we have chloride. So sodium oxide is Na2O, magnesium oxide is that, aluminium oxide is Al2O3, silicon 4 oxide, this is what we did, 2. Phosphorus, we have two phosphorus oxides. We have P2O3, this is phosphorus trioxide. Then we have P2O5, this is phosphorus pentoxide, as we did in Form 1. And then we have sulfur 4 oxide, and then chlorine we have 2 chloride oxide. So these are oxides of elements in period 3: sodium, magnesium, aluminium, silicon, phosphorus, sulfur, and chlorine. Now there are chlorides. We have sodium chloride, magnesium chloride, we have aluminium chloride, we have silicon chloride, we have phosphorus Cl5, then we have sulfur 6. Of course, we don't have a chloride of chlorine. Now, so these are the oxides and chlorides of period 3 elements, their formulas. Okay, starting with sodium. So these and these oxides are metallic oxide. This is metallic: sodium oxide, magnesium oxide, aluminum oxide. These are metallic. Now, sodium and magnesium and aluminium, we say when they dissolve in water, they form acids. They form basic solutions. For aluminium oxide is amphoteric. So this one is amphoteric. Amphoteric means it displays both acidic and basic properties. Magnesium oxide is basic or alkaline. Sodium oxide is alkaline. These other oxides are acidic. They dissolve in water to form acidic solutions. These are nonmetals. Now, this one, sodium and magnesium and aluminium, they form ionic compounds. So this one, the bond is ionic bond, ionic bond, ionic bond. So these three are ionic bonded compounds. They have giant ionic structures. This one, silicon 4 oxide, we mentioned it. It is covalent bond, and the structure is giant atomic structure. So here is covalent bond, giant atomic structure. For the rest of these are simple molecular structural compounds. So these are simple molecular structures. This silicon 4 oxide is giant atomic structure. That is the structure and the bonding of oxides. Again, we have said sodium, magnesium, and aluminium oxides are ionic compounds. They form giant ionic structure. This one is these four here are covalent compounds. They are covalent compounds, and the structures are, for silicon 4 oxide, giant atomic structure. For these others, they have simple molecular structures. So that is the structure. So from left to right, you proceed from ionic to covalent bond. So that is it. Now for chlorides, as we have mentioned, the only special chloride that I want us to discuss here is aluminium chloride. Otherwise, the rest, I think, are as straightforward as we have said for this. So maybe let me discuss aluminium chloride. So this one is ionic, this ionic, this is ionic. Aluminium chloride is kind of molecular. So maybe I can talk about aluminium chloride a bit. Now, the first thing we need to note about aluminium chloride is that it exists as a dimer. existing as a dimer means you have aluminium and chlorine bonding to, this is a molecule of aluminium chloride. So we have 1 aluminium and 3 chlorine. So dimer, forming a dimer, you have another molecule of the same kind. Now these two combine to form this kind of a compound. So aluminium attracts to chlorine like that, so that this aluminium chloride that forms here, it does not exist as a molecule like this. It exists as Al2Cl6, where this is attracted to 3 chlorines by covalent bond. This is covalent bond, covalent bond, covalent bond. And then this one molecule is attracted to the other molecule through dative covalent bond or coordinate bond. This is dative bond, this is dative bond, where chlorine shares its pair of electrons with aluminium, and so to that also. So aluminium chloride exists as a dimer. This is what we call a dimer. So when it dissolves in water, it dimerizes. So we can say it dimerizes in water to form an acidic solution. It dimerizes in water to form an acidic solution. So when it forms an acidic solution, it behaves like a molecular compound. It is not an ionic compound. So thus behaves like a molecular. Behaves like a molecular compound. We expect that ionic compounds that do not form acidic solution, they form alkaline solutions. But in this case, aluminium chloride dissolves in water, it dimerizes, and it forms an acidic solution, making it to behave like a molecular compound. So that is aluminium chloride, which exists as a dimer or molecular compound or molecular structural compound rather than ionic. So this is what we need to note. We also need to remember that aluminium chloride sublimes when heated. Aluminium chloride sublimes. When you name one of the substances which are sublimates, aluminium chloride is one of them. It is a sublimate. It sublimes when heated. That means aluminium chloride, the molecules come together to form a dimer. In the process, it sublimes. So that is aluminium chloride. All right. Okay, so that is it. Now back to this table. So aluminium chloride hydrolyzes in water. All of these hydrolyze in water. To form So these ones hydrolyzes in water to form acidic solution. These three, because they are molecular. So we have said aluminium chloride behaves as a molecular structure. Similarly, these are molecular structures. So in so doing, they hydrolyze in water. Hydrolysis is actually the breakdown of a substance using water. It is where when you dissolve this in water, it breaks down and then it forms an acidic solution. So that is on these chlorides. Otherwise, for sodium and magnesium, they dissolve in water to form solutions. So acidic solutions, when you remember acids, we said acids have a proton, they have hydrogen ion. And sodium chloride, when they dissolve in water, there is no hydrogen produced. Maybe we can write those equations. Aluminium we have aluminium chloride in water to form aluminium hydroxide and HCl. Okay, this is solid. Sorry, this is also a solid. And then this is 3 and 3 here. So that is for aluminium. So we are saying the solution is acidic because later on this hydrogen chloride form, it will dissociate. When this one dissociate, you have HCl. It dissociates to form hydrogen ions and chloride ions. So the presence of these hydrogen ions makes the solution acidic. So that's why we are saying this one hydrolyzes in water to form acidic solution. The other one is silicon. Silicon chloride. Silicon chloride forms silicon oxide and HCl. This is a solid, this is a liquid. Hydrogen is you have 2 and 4 there. So as we said also, this one breaks down or dissociates in water. So you have HCl. When it dissociates, you have hydrogen ions and chloride ions. These ones, the presence of hydrogen ions in the solution renders the solution acidic. So that is it. The same thing to phosphorus and sulfur. Okay. Okay, for sodium chloride and magnesium chloride, because they are ionic compounds, when they are dissolved in water, then you will have sodium ions and chloride ions. This is because they are ionic compounds, so they dissolve in water to form sodium ions and chloride ions, and similar to magnesium. So because we don't have hydrogen ions, in this case here we don't have hydrogen ions, we don't have hydroxide ions, so the solution is neutral. If there were hydroxide ions, the solution is basic. If there were hydrogen ions, the solution will be acidic, just as we have said here. The presence of this HCl, the HCl dissociates to form hydrogen ions, which renders the solution acidic. Similar here. So you find in this case that you have aluminium hydroxide, but the presence of this hydroxide, as we have said, when this dissociates, it gives hydrogen ions. You remember, this one is a solid. This one is a solid. So that means you do not have hydroxide ions. It is a solid aluminium hydroxide. So that is it for the chlorides of period 3, as we have discussed. So that brings us to the end of structure and bonding. Those are 3 lessons. All you need to remember is the types of bonds that we have said, the types of structures they form, and the examples, the illustrations that we did. And then you also need to know the properties of those compounds, properties of ionic compounds, properties of covalent compounds, properties of metallic compounds. So when you do that, I think we have a good time. Okay, so maybe I can leave you with some assignment to do. Number 1, and diamond allotropes of carbon. The first question, define allotropy. And 2, explain why diamond has a higher melting and boiling point than graphite. The melting point of diamond is 3500 degrees centigrade. The boiling point of graphite is 2238. So find out why there is that difference. Lastly, number 2 is in terms of structure and bonding, explain why silicon oxide has a higher boiling point than carbon 4 oxide. Okay, so that is your assignment to wind up our lesson on structure and bonding. Define allotropy, and then you explain why diamond has higher boiling point than graphite. So that is it. Otherwise, I want to thank you for being around, and watching our lessons. We will continue doing this, so we find a topic for next week or our next lesson on Wednesday. Otherwise, until then, I wish you good luck. I wish you good health, and God bless you. Bye bye.